Problems with wedges can be dealt with using friction. In this particular example, we have a block sitting on a corner here with a wedge under the other corner. We're told that the coefficient of static friction is 0.3, and that's between all surfaces, so between the block and the ground, between the block and the wedge, and between the wedge and the ground. And we're asked to find the minimum value of P to remove the wedge here. In so doing, we are also assuming that the block does not slip at point A. One of the first things to do here is to separate the objects into two separate free body diagrams. So I'm going to draw a free body diagram of the block itself. I'm also going to draw a free body diagram of the wedge. The piece of information I know is the mass of the block, so I'm going to use an auxiliary computation to calculate its weight. And the weight of the block will be applied at the center. Now I'm also going to need to apply normal and frictional forces to each of these objects. I'm going to start with point A. At point A, we have a normal force acting perpendicular to the surface. We also have a frictional force over here. Now I don't know which direction it's going, and I don't know its value. The only thing I can say about this frictional force is that it is less than or equal to μs times NA. How do we know that? Well, at the beginning of the problem, you were told that there was no slip occurring at point A, which means that whatever this frictional force is, it has to be less than the maximum friction, because if it was more than the maximum friction, then it would be slipping at that point, so it has to be less than or equal to that maximum friction. Now over here at point B, we also have a normal force and a frictional force. The directions of these are important. We have to make sure that we're assuming them properly. The normal force at B is pushing up, and it's acting upwards at an angle because the wedge is at an angle. We also have our frictional force here acting on point B. And the direction of that frictional force is important that you realize. If the wedge is being pulled out towards this direction, towards the right, the block is sort of moving towards the left. Friction has to oppose motion, and so therefore this frictional force has to be going towards the right. And I know that that frictional force is going to equal μs times NB. How do I know that? Well, anything greater than that and the object's going to be moving. So as long as we don't exceed that value, we can apply P and the object will not move. Now, if you have a hard time seeing that this frictional force is going in this direction, I suggest you look at the wedge. We have two frictional forces acting on the wedge. We have Fc, which is the friction between the wedge and the ground. I'm calling that sort of point C. And we have Fb, which is the frictional force between the wedge and the block at point B. The problem stated that we are pulling the wedge out. If that is the case, all frictional forces have to oppose that motion, and the only way for that to occur is for Fc and Fb both to be going towards the left on this wedge free body diagram. Remember that friction never helps motion, it always opposes motion. If Fb is going towards the left on this diagram, it has to be going towards the right in this diagram, because when we put those two pieces back together, the forces have to cancel. Likewise, since NB is pushing up at the bottom of the block, it has to be pushing down on the wedge. Now NC we can assume in either direction. It's going to be going perpendicular to surface, meaning NC will be a vertical force, but the only thing that makes sense logically is for NC to go upwards. So now we have our free body diagrams both drawn and complete. We've got our wedge, which has a normal force acting between it and the ground, as well as a normal force acting between the wedge and the block. There's a frictional force between the wedge and the ground, and a frictional force between the wedge and the block. On the block, we have the weight of the block. We have a normal force pushing up at point B at an angle because the surface of the wedge is at an angle. Remember, normal means perpendicular to the surface. Since the surface is angled, the force is going to be angled. And we have a frictional force. Make sure that the senses of these and the two forces over here agree such that when we put it back together, they cancel out. And then over here at point A, we also have a normal force and a frictional force. Going forward, we're going to need to use static equilibrium to solve the problem. And you can start with the block or the wedge. Either way would be valid, but there's only one way that'll actually allow you to come to an answer easily. And that is starting with the block. Now you might wonder why that is. Well, if we look at the wedge, we don't have any knowns in the wedge. We don't know NB, we don't know NC, we don't know FB, we don't know FC, we don't know P. That is a pretty good indication that we're not going to be able to solve that thing. There are 1, 2, 3, 4, 5 unknowns. Over here on the block, there is one thing that we know. We know W. Now we don't know FA, NA, FB, or NB, but because we know W, we can actually solve this particular diagram. Now the next question is, okay, that's where we're going to start. How do we solve it? The best way to solve this block is to say, well, FA and NA don't really have anything to do with the rest of this problem. If I can just find FB and NB, I can transfer that information to the wedge and then solve for P. What I'm going to do is I'm going to apply static equilibrium to moments with respect to point A. That's going to cancel out FA and NA. Then I'll be able to use W to solve this problem. Whenever a problem has more than one free body diagram like this, you should really be specific in your headings saying which free body diagram you're using. So first I'm going to state static equilibrium assumptions. Next I'm going to write my zero statement. In my zero statement I want to cross out everything that's not going to produce a moment around point A. So FA will not produce a moment because its perpendicular distance is 0. NA will also not produce a moment. FB's x component is right here on this blue line and it goes through point A, so FB's x component will not produce a moment. Likewise, NB's x component is right here and it's not going to produce a moment around point A. So then I just have three terms left in my equation, W, FB, and NB times each of their perpendicular distances. W is going to produce a negative moment around point A and its perpendicular distance is A. You might look at this equation and think you have two unknowns. You don't know FBY and you don't know NBY. But actually there is really only one unknown because FBY is going to produce a positive moment and the value of FB is mu s times NB. That's FB. So we really only have one unknown. We only have NB. Its y component is mu s times NB times the sine of beta. And its perpendicular distance for FB, it's right here. Its perpendicular distance is A plus B. NB's y component likewise is going to produce positive rotation around point B. And the value of NBY is NB times the cosine of gamma times its perpendicular distance, which is A plus B. So now we can pull out a common NB and solve this equation. Solving for NB, we will get, now we can plug our numbers in, and we will find that NB equals a positive 2383.13 newtons. So that means the sense of NB agrees with what we have drawn in the diagram. The sense of NB also agrees with what we have drawn in the diagram on the wedge. I now know FB and I know NB. I can find both of those. They're no longer unknown. Now, if you wanted to, you could take FB and NB and solve for FA and NA at this point, but they have nothing to do with the rest of the problem. We're looking to find P. So the next thing you want to do is take that information for FB and transfer it onto the wedge. So we know FB, we know NB. Now let's look at some of the forces in the x direction, some of the forces in the y direction. If we sum forces in the x direction, how many unknowns do we have? Well, I know FB. I don't know FC, and I don't know P, so there's two unknowns in the x direction. If we look at the y direction, I know NB, I know FB, I don't know NC. There's only one unknown in the y direction. So the best thing to do now is to apply static equilibrium to forces in the y direction. FC has no y component, likewise P has no y component. However, FB, NB, and NC all have y components. The value of FBY is a negative mu s times NB. That's FB. Its y component is that times the sine of beta. NB's y component is a negative NB times the cosine of gamma. NC's y component is a positive NC. Solving this for NC will give us this. Now we can plug the numbers in. And you'll find that NC equals a positive 2452.50 newtons. So now that we know NC, we can sum forces in the x direction. Since FC is just a function of NC, I now can use that to find P. So I'm going to apply static equilibrium to forces with respect to x on the wedge. There's only one of these forces that does not have an x component, and that is NC. So FC x component is a negative mu s times NC. FB's x component is a negative mu s times NB times cosine of beta. NB's x component is a positive NB times sine gamma, and P's x component is a positive P. Solving this equation for P gives us this, and now we can plug the numbers in, and you will find that P equals an 1154.93 newtons. So at the end of the problem, that value for P goes in the box. That's the amount we would need to use to pull the wedge out. Just as a quick final note, if P turned out to be a negative number, the wedge would have to be held in place rather than pulled out, because its tendency would be to pop out from under the block.